Let's write down some properties of double integrals. Each one of these is a theorem, okay? And we're not going to prove hardly any of them. But for each and every one of them, I want to give you the intuition. So I want you to be able to see, to agree that they make sense, that they compile. And the intuition that you have for double integrals is volume under graph, right? So whatever I write down should be consistent with the intuition of volumes under graphs. Okay, the theorems are more general because functions are not necessarily continuous and not necessarily positive, and the double integral has more uses than just volumes under graphs, but whatever I write down should at least be consistent with that intuition. Okay? And what you should also see is that each and every one has a counterpart in single integrals with one snake that you already know. Okay? None of these should be new in any sense. So here's the first one. If f is continuous on D, then the integral, the double integral on D of fxy exists. Well, after the introductory words about you should be able to see the intuition behind everything, well, this one is actually not one of those. We defined the double. We never wrote the definition, in fact, right? We only gave the intuition for double integrals, and the integral could exist. The formal way of saying is f is integrable. Okay, so f could be integrable, meaning that this limit exists. Remember, the integral is some form of limit, right? It's the limit of the Riemann sums, and limits don't always exist. Okay, so that's a kind of a route of exploration that we're not taking. When does that limit exist or not? But for good functions, for continuous functions, it always does. The volume under the graph always makes sense. Okay, so that's this statement. It's true for Calc 1 as well, and it's not an if and only if statement. And you know that. Okay, so maybe let's even write it as a second theorem. If f is, so think of Calc 1, for example. Can you think of a function which is not continuous, for which the integral from a to b does exist? Right, a step function, for example. Do you agree? A step function, there's no issue whatsoever of calculating the area under the graph, but it's not continuous. Do you agree? Okay, so the same thing is going to happen here. We are going to allow some discontinuities, and still this volume under the graph is going to make sense. Okay, so that's going to be this statement, but in functions of two variables, it's not just a step function. It can be more complicated, and in fact, f could have, for example, finitely many points of discontinuity, and it's still going to be continuous. F can be comprised of a collection of finitely many continuous functions on subdomains of D, and is still going to be continuous. Okay? F could have infinitely many points of discontinuity. For example, it can be not continuous on a certain curve in the domain. A curve has infinitely many points, and still it's going to be continuous. Okay? So I'm not going to be precise here. I'm just going to write if f is almost continuous. And this is not just an informal word. One can formalize this, and there is a notion of being continuous almost everywhere. Okay? It's a formal notion, but we're not going to formalize it. Okay? But the idea is that it's almost everywhere continuous. Okay? Then f is integrable. Integrable meaning the integral exists, meaning there's a limit to those Riemann sums as we refine partitions. F is integrable on the domain D. Okay? And these are the only functions we're going to be considering in this course throughout. Okay? We are not going to be dealing with the very interesting to mathematicians pathological situations, or they're not even pathological, but the situations which are interesting to mathematicians and usually not relevant to people who use mathematics in applications, whether it's in other sciences or engineering, usually encounter continuous or almost continuous functions. Okay? Okay. 3. And for the remaining of the theorems, I'm going to add a line here that's going to be relevant to all of them. Assume f and g are integrable. And if this word scares you, just think of continuous or almost continuous functions on D, on some domain D. Okay, so 3 says the double integral of alpha f plus beta g, and allow me to write it without the xy dx dy in order for it to be shorter and more easy to grasp and remember. All these x's and y's sometimes blur things. Equals alpha times the double integral of f on D plus beta times the double integral of g on D. This is called linearity. Okay? It respects sums and it respects multiplication by scalars. So alpha and beta here are just scalars. Okay, good. And this is called linearity. Linearity of this this action in algebra. You're going to call it a linear operator. Okay, this double integral is a linear operator. Okay, it's linear. Clear? Okay, 4. So this is linearity. The fourth property is called monotonicity. For functions of 2 variables to be monotone, that doesn't really compile. We discussed that, right? What do we mean by saying that a function of 2 variables is monotone? In which direction does it always go up or always go down? It doesn't really make sense. But that's not what I mean here. I mean that this operator is monotone. So what do I mean by that? If f is less than or equal to g on any point in the domain, so f and g is bigger, then the integral of f is going to be less than or equal to the integral of g. Do you agree that this is obvious in terms of volumes under the graph? If this is the graph of f and this is the graph of g, the volume under the graph of g is going to be bigger than the volume under the graph of f. Does everybody see that? Okay? And it's the monotonicity of this operator, the integral. So this replaces 2 points here. X is less than y, then operator of x is less than operator of y. F is less than g, integral of f is less than the integral of g. That's being monotone. Clear? Is it clear why I'm using this word? Okay. Property number 5. I'm going to write a non-theorem, but it's important to write it because it's kind of a common mistake. No formula for the integral of f times g. Okay, so it's not true in particular that the integral of f times g is the integral of f times the integral of g. That was not true in Calc 1 either. Okay, so I just want to highlight this because it's kind of a common mistake. Good? You know this, right? Okay. Property number 6. the absolute value of f is integrable, and satisfies the following inequality: the absolute value of the double integral of f is less than or equal to the double integral of the absolute value of f. Again, this theorem has, you can remove a snake and it will remain true. Since I didn't write fxy dx dy, writing the single variable counterpart is just erase a snake, right? And you should know this. Why is this true? Let's hand wave it a bit. What do we have? First of all, for this to be in any way interesting, f has to be not always positive, right? Because if it's always positive, then the absolute value of f and f itself are the same, and this is going to be an equality. Do you agree? Okay. But if f is not always positive, so think of this as the xy plane, the graph of f is sometimes above the xy plane, and if f is not always positive, sometimes it's below, right? What's the absolute value of f? The absolute value of f, whenever it's below, we flip it, right? The absolute value, fxy is down here. In absolute value, it's going to become up here. So instead of having mountains and valleys, we're just going to have a bunch of mountains. Okay? Do you agree? And that's the absolute value of f. The integral of that is just going to be the sum of the volumes of these mountains. Do you agree? When we had a valley here, it's going to become, under this, a mountain, and the integral is just the sum of the volumes of these mountains. Do you agree? Everybody see that? Whereas in this side, we're first taking the integral, so now there are mountains and valleys, and the integral sums the area, the volumes of the mountains minus the volumes of the valleys. Do you agree? Because for the valleys, it gives the volume above the graph, but with a minus sign. Does everybody see that? So we're going to have here kind of cancellations of pluses and minuses. We're going to get a smaller number here, and then we're going to take it in absolute value. Clear? So this thing, because of the cancellations, is going to be volumes minus some volumes, plus volumes, minus volumes, plus minus volumes, whereas this is just going to be taking all the volumes in plus. This is obviously bigger. Clear? Intuitively, is it clear? Everybody? Okay. Property number 7. The double integral of f on a domain D is less than or equal to, let's call it capital M, bless you. So this capital M is going to be the maximum value of f on the domain D. Is what written here clear? Okay, is what I wrote here clear? Okay, I'm taking the maximal value on D of fxy. Okay, now remember that f is continuous or almost continuous. You can write supremum rather than maximum, but let's assume f is continuous, and it does it's bounded. In fact, it's bounded. There is some maximum. Okay, and let's assume that it actually attains it. Okay, let's assume that it's continuous. Okay, now even for single variable calculus, you have the area under the graph. It's less than if you take the area under the maximum. Do you agree? Think double variable. You have the graph. Here's the graph of f. Up here. Do you see it? See it? Here's the xy plane. F has some maximal value. There it is. If you replace the integral is the area under the graph, with the maximal value times what? What's missing here? I have to add something here. the area of the domain, very good, times, let's write it, the area of D. Oops, I smeared D. So if you take the area of D down here, multiply it by the maximal value of the function, you're going to get a box shaped like D, and the volume under the graph sits in there. Do you agree? Everybody see that? And what's it going to be bigger than? Right, take the minimal value. So little m is going to be the minimum of fxy in the domain times the area of D. Okay, does everybody see this? So this already allows us some ability to approximate, but it's very, very rough. It's not a good approximation. Okay, if you take a function and the volume under the graph may be very small, okay, like the volume of the I don't know, of the under all the buildings in Paris. Okay, what's the volume under all the buildings in Paris when you look at the area of the municipal Paris? And what you're going to get here is the height of the Tour Eiffel times the area of Paris. That's not actually the volume under all the buildings, right? It's much, much bigger. Do you agree? Okay. Okay, so we still don't have any tool of calculating. We're down to theorem number 7, and we still don't have any idea how to calculate, right? Useful theorems, but still no hint at calculating. Okay, theorem number 8. Let's write it here. So this is what I said in the previous clip. We're going to be listing here a bunch of theorems which kind of help us understand this notion, and they're useful. We're going to be using them in things we do, but it's still, all of them are not going to tell us in any way how to calculate integrals. For that, we're going to need something else. Okay? So here's a tricky one. If f is continuous, on D, and D, let's say that D is connected. Then, so I want to think of a domain which is a connected domain, and this kind of hints, the only place in this course where we actually looked at connected domains, where that played a role, was with the intermediate value theorem, remember? So this is, number 8 is going to be related to the intermediate value theorem, and in fact it's sometimes called the intermediate value theorem for integrals. And it has a single variable counterpart as well, which I hope you met. So if f is continuous on D and D is connected, then the integral over D of f, oh, I wrote the entire thing, never mind, equals, now you should be very excited, right? I'm going to tell you how to calculate it, but not really, equals the value of f at some point x0, y0 times the area of D. And this x0, y0 some point in D. So first of all, do you agree that this does not tell us how to calculate things because we don't know what point in D? Okay, so it's kind of an existence theorem, but it doesn't tell us how to do it. If we knew what this point was, we'd be done. We would know how to calculate integrals. Okay, but this theorem just says that there exists, maybe I should add here this existence sign, there exists some point in D such that the integral equals the value of f at that point times the area. Okay? And why does this make sense? Well, by the previous theorem, here's the graph of f. If we take the maximum, then it's an upper bound. The maximum times the area of D is an upper bound for the volume under the graph. The minimum times the area of D is a lower bound for the area under the graph. And there exists some value such that if we take the value of f at that point, there exists some point such that if we take the value of f at that point, we get precisely the value of f times the area gives precisely the integral. Okay? Let's prove this. Let's prove number 8. The idea of the proof is, do I want to prove it? Let's not prove it. I don't want to scare you. It's not a scary proof. Let's do this. Try it on your own. Okay? And I'll tell you what the tools you should be using are. Okay? It's not hard. It's easy. But it's going to bring back the intermediate value theorem for continuous functions on connected domains. Okay? Try to prove it. So you're going to be using the previous theorem. Let's look a second at this board. You're going to be using the fact that the integral is between these two values. Okay? I'll tell you the idea of the proof, and then you can write it down and see if you agree. Look at this a second and divide this inequality by the area of D. Okay? Divide it out by the area of D. You're going to get little m is less than or equal to the double integral over the area of D, and is less than or equal to big M. Do you agree? Everybody with me? Okay. Now in here, in between little m and big M, is now the double integral over the area of D. Do you agree? That's a number. Do you agree that that's a number? The double integral is a number. The area of D is a number. So it's some number between little m and big M. Do you agree? Everybody with me? The intermediate value theorem says, for just regular functions, this is some number between the minimum of the function and the maximum of the function, right? So there should be a point where that number is actually attained by the function. That's the intermediate value theorem for a function of two variables on a connected domain, a continuous function. Do you agree? So there should be some x0, y0 where the value of f at x0, y0 is that integral over the area. Do you want me to write it? You got it, right? Let's write it quickly. Proof, real quick. By 7, by the previous theorem, we get that little m is less than or equal to the double integral of f divided by the area of D. And this is in turn less than or equal to big M. Do you agree? Okay. This is some number between the minimum of a continuous function on a connected domain D and the maximum of a continuous function on D. Therefore, there exists some point, x0, y0, such that the value of f at that point equals this number, the double integral of f divided by the area of D. The intermediate value theorem doesn't tell me where this point is, it just tells me it exists. Do you agree? Everybody good? Now multiply by the area of D, and you get this. Clear? Good? Okay. Questions on number 8 and the proof, which I didn't mean to do, but happened. I did it. Everybody good? Okay. 9. So we did the intermediate value theorem. Let's erase here. 9 is a property called additivity. And it says the following. additivity if D is the union of two domains, and leave a little space here. We're going to need to add something. Leave a little space. Then the double integral of f on D equals the double integral of f on D1 plus the double integral of f on D2. Now tell me intuitively, does this make sense? It makes sense. So why did I say we need to add something? You should realize, if you think for a minute, that this cannot always be true. Something here is not accurate. Say that again? Absolute what? No. It doesn't have to do with absolute value. No. Very good. When I write that D is a union of two domains, it doesn't mean that they're separate, right? D1 can be, for example, contained in D2 or intersecting D2, right? So if we look at the volume over D1 and add, the volume under the graph over D1 and the volume under the graph over D2, if they intersect, we're going to be counting the volume under the intersection twice. And the volume under the union is not going to be the sum, it's going to be the sum, but you have to subtract the volume over the intersection. Do you see that? Okay. So this is true only if D is the union of D1 and D2, and either they don't intersect at all, or they could intersect on, let's say, a curve, or some intersection which does not have an area. So remember, for example, in single variable integration, the integral over a point is 0, right? The integral from a to a of f is 0, right? Everybody know that? So the double integral is going to be 0 whenever you take the integral over a domain which is one dimension less. So if you take the integral over a curve, not over an area, over a curve, that integral is going to be 0. Okay? So if D equals D1 and D2, and the intersection of D1 and D2 is either empty, that would mean that they're completely separated, or that the intersection of D1 and D2 is, again, I can formalize this, but I don't want to spend time on formalizing this. So let's just say the intersection is of 0 area, Then, and 0 area means it's either a point or finitely many points, or a curve, okay, a smooth curve, for example, is going to be of 0 area. Clear? Is it clear what I mean by 0 area? Okay, so for example, if this is D and you break it up like this into D1 and D2, that's fine. Their intersection is of 0 area. So the volume over the intersection is going to be 0. So you're not counting volumes twice. Is it clear? Is the idea clear? Everybody? Okay. Good. So I think this sums up the theorems that I wanted to mention, the properties. Any questions? So after all this list, it's very obvious that we don't know how to calculate integrals yet. Does everybody agree? So there's going to be a theorem 10, but it's going to have a clip of its own, And that's going to be in the next clip of how do we actually calculate integrals. Coming up next.